So now that we've learned about bias variance, let's see how it manifests in overfitting. Here we have a quadratic function which we've sampled some data points for, but the observations are slightly noisy. That means we have a noisy target, as you can see, because the observations don't quite line up for a couple of the points. So to learn this function, we're going to apply a fourth-order polynomial fit. A fourth-order polynomial has 5 degrees of freedom, should be able to capture this exactly. So what do you think is going to happen? Well, because we can fit the points exactly, we're going to have no training cost, but you can see here the test cost is huge. All the yellow areas indicate a case where there is some mean squared error being applied because the predicted value is off. For example, very close to the ends of the graph, there's a lot of squared error here, and also in the middle. The problem here is that we're not just fitting the data that's provided, but we're also fitting the noise. In fact, the noise is indistinguishable from the data, so we can't determine which parts of the signal to try to fit. So we can define overfitting as fitting the data more than is warranted. And this has to do with the quality of the data resources as well as the quantity, as we saw in the last part on bias variance. The culprit here is that we're fitting the noise, meaning not just the data, but other pieces of information that is inherent with the selection of the training data set. We might think that that's not so bad because fitting the noise might be useless, but it's not the case. In fact, fitting the noise can cause us to get significantly off of our prediction values that we would have otherwise, and it can be quite harmful. Let's take a look at a case of trying to fit two different target functions. On the left, we have a 10th order target function. That means a polynomial with terms up to x to the 10th, all the way down to a simple intercept or bias term. But we're going to wiggle a little bit and say that there's some noise in the observations. As you can see here, the blue line is the target function, and the observed values are off of that line because of the noise that we observe in a target. Let's take a look at another function that we might try to fit. Here there's a 50th order target function that's noiseless. We're going to observe the actual target values exactly as they are. As you can see, all the data points on this right graph are exactly where they're supposed to be on the line itself. So we have case A and case B here. And we want to ask ourselves what will happen when we try two different types of polynomial fits. Let's restrict ourselves to the case of where we use polynomials of up to second order, meaning a quadratic curve, or 10th order polynomial. Of course, now that we've learned about bias variance, we know that the lens of the data set that we're providing will dictate the quality of the results somewhat. Here we're given 15 data points to fit our curves. Before we go ahead, think about which of these two models, the second order or the 10th order, would be suited for either the A model or the B model. You can pause this video. Write it down somewhere before you continue to the next part. In case A here, we see that the second order polynomial tries its best to fit the data points, but of course it can't do so very well. It tries to average out the errors, of course, to minimize mean squared error. And as expected, it's going to have some loss in fidelity. Its test performance isn't much better, and of course should be higher because we don't have a chance to fit to the data. What about the 10th order? Of course, by having more degrees of freedom, we can see that the observations line up better. It can get many of the data points quite close to accurate. The problem here is, even though we get a lower training cost, we're going to get a very high cost in testing. And we can see why by overlaying the target function, which I'll just try to draft. You can see where the H10 hypothesis goes quite close to vertical, that the squared error term is really going to jump. What about in the case of the noiseless, high-order 50th order polynomial target function? Which one does better there? We might think just because we have a noiseless target function that the story might be different, and predict that using a 10th order polynomial might be better. Well, we're sorry to disappoint. Again, you can see the same type of problem is occurring. Let us again plot the lines of where the 50th order polynomial would actually go, as composing the last slide with this slide. Again, we can see where the 10th order polynomial goes pretty much vertical, we have a poor result. And this means even though we get a very good fit for the 15 points that we have in our training data, we're really going to blow it when we come to our test data. Let's take a final case and try to think of it a bit more closely. Here we have the case again of two learners. We're going to call one that's overfitting and one that's restrained, O and R for short. Here we're going to tell both of our learners that the target is indeed a 10th order polynomial, but this time without noise. Do you think the tables are turned now? We're still going to provide only 15 data points. Our overfitting learner will choose H10, and our restrained learner will choose H2. The question is, just like before, is who is going to win this match in terms of mean squared error on the test data? Think about it, and we'll go over this again in our post lecture.